Last time we started working in section 3.2, and we were talking about algorithms, which are methods for doing addition and or subtraction. We've gotten through all of our methods. The last part of this section that we haven't done yet talks about doing addition and subtraction in other bases. Now, there are times when I teach, and I didn't really feel like you guys did this to me very much, but there are times when I teach these other methods and sort of eyes glaze over because you look at this and you say, addition and subtraction, the way I learned it, worked fine. There's really not, I don't really see the purpose behind having all these other methods. And I understand that to a degree, but you also have to understand, of course, and as we talked about in classes, that you don't know where your students are coming from. Working in other bases helps put us in that position of those other students. And so that's what this point of the last part of this lesson is we're going to take a look at some of these methods that we've discussed and how to use other bases to sort of put ourselves back in the position of what that first grader or that second grader is feeling when we talk about addition and subtraction in this way. So let's talk first about, first remember that when we're talking about base 8, it has certain digits. What are the digits in base 8? Close. 0 through 7. Yeah, we want to remember that we have the number 0. So 0, 1, 2, 3, 4, 5, 6, and 7. So no 8s in base 8, no 9s in base 8. And so we're going to take a look at 3, 4 base 8 plus 1, 7 base 8. And I want to talk, we'll do our standard algorithm first so that you can kind of see what this looks like. And then we'll do one of the other algorithms for the addition instead. So this is 3, 4 plus 1, 7. Okay, so in our standard algorithm, we would add the 4 and the 7 together first, right? 4 plus 7 is actually the numerical value 11. Well, there's not an 11 as a single digit. In our system, we would have written the 1 down, and we would have carried the 1, right? Okay, and we would have done that because there was 1 10 and 1 leftover 1. That's what the 11 would mean. 11 is 1 10 and 1 1. That's why we would have written them down in that way. But this is base 8, which means I want to figure out what 11 is in terms of base 8 and how many leftover ones. So if I have the number 11, how many 8s is that? It's 1 8, right? With how many left over? 3. Okay, so we talked about this once before, but let me remind you, it's like having the 11 crayons on the floor and you're wanting a bag of 8 of them. So you get 1 full bag of 8 and you get 3 leftovers. Okay? So we're going to carry the 1 full bag of 8 to the next column because that's the 8s column. I have 1 8. And then I need to write down the leftovers that I still have of the crayons on the floor. I have 3. 1, 3, and 1 adds up to the number 5, and that's in base 8, so we're good to go. So this is actually 5, 3 base 8. But see, you have to actually stop and think about what carries over. And it's carrying over because it's enough of it to be 8 items. Are you with me? It's a little bit tricky because that's not how we usually think about our addition. We just usually plop a number over there, don't we? All right, so let's think about what happens then if we do this in a different way. Let me cut this out. I want to do this with scratch addition, not because it works especially well, but because scratch addition is a little bit complicated and sometimes it feels a little bit awkward. When I add the numbers 4 and 7 with scratch addition, one of the ways to do that is to think about counting up from the number 7, okay? So we're going to take the number 7 and we're going to add 4 more to it. Well, if we do 7 and we add 1 more to it, we're at 8, right? So when we did this before, once we got to 10, we scratched. Do you remember that? Once we hit 10 items, we scratched. Well, when I'm doing 4 plus 7, I've got more than 10 items, so I scratched it. So I had 7, and I added 1 more, and I got 8, and I scratched. How many more have I not added yet? 3. Okay? So there's 3 more that I would need to add after the scratch. The scratch represents 1 8. So it's carrying the number 1, giving me the number 5. Same answer at the bottom, but we thought about it in a slightly different way. Again, scratch works a little bit, well, not a little bit. It's more efficient to use when you've got a list of numbers. This is only 2 numbers, so I recognize this is a little awkward on this one, but any questions on that one? Okay. Let's do a subtraction one. Same numbers, 3, 4, and 1, 7, but we're going to subtract them. All right, so in our number system, when we subtract and we don't have enough to subtract somewhere, one of the ways to do that with a standard algorithm is to borrow numbers, right? And when we borrow from the column that is directly to the left, how many are we borrowing? We're borrowing 10 because it is the tens column. But this is base 8. So this is not the tens column, it's the eights column. So when I borrow in base 8, I have to borrow 8 because it is the eights column. So when I take this number 3 here, I turn it into a 2 because I'm borrowing one of those values. But one of those values has a value of 8. Have the 8, I have the original 4. What is 8 plus 4? How many total is that? That's 12, okay? So just like in our system, we can actually write a number that's too big for the placeholder just right there. We do that all the time, right? If we were to borrow, if this number were in base 10 and we borrowed, we could have scratched the 4 and written 14, right? So it's the same thing. So I'm still perfectly fine with you writing the number 12, even though it's too big for the base. That's not the problem. But you actually have the ability to subtract now. What's 12 minus 7? Plain old 12 minus 7. What is it? 5. And what is 2 minus 1? 1. So this is 1, 5, base 8. Okay, let me show you this in one other way then. I think it was like maybe the last method we even came to was a method called equal additions. Do you guys remember that? Where we added things to one number so we avoided borrowing. The whole idea is to avoid borrowing. Well, the number 1, 7 is awfully close to being too big to be a 1 and something else number, right? It's the biggest 2-digit number that starts with 1 in base 8 because I don't have a 1, 8, okay? So if I were to add the number 1 to the number 1, 7, what would I get? What comes after 1, 7? 2, 0. Do you guys remember that? I mean, it's been a while since we actually wrote these numbers out. But when we run out of digits in our system, like 1, 9, we change the first digit to one larger, the number 2, and we zero out the last digit. So the same thing happens in base 8. But if I add the number 1 to the bottom, I would add the number 1 to the top. So what's 3, 4 plus 1? 3, 5. How's that for subtraction? What's 3, 5 minus 2, 0? It's 1, 5. No borrowing needed. It's actually really nice and clean. This is a really good example of one where I think equal additions is easier on this one. Because that number 1, 7 was so close to simply moving it to being something I don't have to borrow from anyway. It's actually a really nice one to use with equal additions. Let's try another one. Let's do base 3. Do you know what the digits are in base 3? Good. 0, 1, and 2. All right, so we're going to add in base 3. These numbers are a little larger than the last problem that I just did. We have 1, 2, 1, 2, and 1, 1, 2, and we're adding them together. We're going to do standard algorithm because I want you to understand that the standard algorithm is more difficult when you have not done it forever. And that's what this looks like and feels like now because you're not working in your base system. So let's take a look. I have 2 plus 2. What's 2 plus 2 normally? It's 4. Do I have a 4 in base 3? I don't. So what is a 4 in base 3? Well, the question is how many 3's is it and how many 1's is it? So how many 3's is this number? It's 1, 3 plus 1, 1, isn't it? The number 4 is 1, 3 plus 1, 1. So, and the reason I'm doing it in 3's is because it's base 3. And I'm taking a look at it in this way because this column where currently I have a 1 and a 1, this column is the 3's column, isn't it? Right? The 2 and the 2, this is the 1's column, and then I have the 3's column, and then I have the 3 squared's column, and then 3 cubes column. Right? Those are the placeholders I have, all in base 3. So when I add 2 plus 2, I get 1, 3, and 1 extra. So I carry over 1, 3, and I write down the 1 extra. Now I have 1 plus 1 plus 1, which is the number 3. That's too big. I don't have any 3's in base 3. So the number 3 in base 3 is how many 3s? 1, which is what I'll carry over. And how many are left over? 0. Now I have 1, 2, and 1, which is the value 4. We already did this one, right? We don't have to do it again. The number 4 should be the number 1 and then 1. So 1, 3, and 1 left over. And then my far column now, where I've got the 3 cubes column, what is 1 plus 1? 2. We don't have to do anything with that because that's actually a number in our base. And this is base 3. Remember, just like we did before, that when you end up with a value in a different base, you need that subscript next to it. Let me show you a lattice method for this, okay? So in the lattice method, we have 1, 2, 1, 2, 1, 1, 2, and then we made this box underneath. Do you guys remember the lattice one? And we drew some diagonals to our box. We still, when we're doing this, and in fact in doing this we can actually add left to right or right to left because of the way the lattice works. So just for fun, let's go left to right because that's kind of unique that we could be able to do this. This number 1 would come straight down and it would go in the bottom box. Okay? So these boxes split how many 3s are on top and how many 1s are on bottom when I add the digits together. So 2 plus 1 is the number 3, which is 1, 3, and 0 1s. 1 plus 1 is the number 2, so that goes in the bottom corner. And 2 plus 2 is the number 4, which is how many 3s? 1, 3, and 1, 1. And then with the lattice, what we do is we add along the diagonals. Now, unfortunately, I think when I did one before, I didn't have this happen, so I do want to show you an example that it can happen. We can still end up adding a number to be too big and having to do something like moving it over. So if you notice the bottom right-hand corner, that's the number 1, right, because there's nothing you're adding together. The problem is that the next sort of diagonal column says 1 plus 2, which is 3, which is 1, 3 carried over to the next column, and 0 1s. I carried it to the wrong column, sorry. Here's my carried over column, and here's 0 1s. So you just carry it to the next, I say column, the next diagonal over, just like you would carry it to the next column over when we carry things over as well. Now I have 1 and 0 in that column, which is the number 1. I have 1 and 1 in the next diagonal column, which is the number 2. So I only had to do the carrying once, and it works the same way as you do in our standard one. This is 2, 1, 0, 1, base 3. Any questions on that one? All right. One more, subtraction. And we have the same base, base 3, 1, 0, 0, 2, minus 1, 1, 0. Let's do standard algorithm first. So in the standard algorithm, we start on the right-hand side. I've got 2 minus 0. That's just fine. I've got 2. And there's a problem, though, right? I can't do 0 minus 1, and I've got 2 of them in a row I'm trying to do. So I would attempt, where the first 0 here is next to the 2, to borrow from this 0. Well, that's not going to work. There's nothing there to borrow from, so we have to do the borrowing one more over. You guys do this with our number system before. So this number 1 right here is going to become the number what? 0, because it's being borrowed from. But when you borrow in base 3, how many are you borrowing? 3. So the original 0, this 0 right here that just crossed out, becomes 3, because I borrowed 3 from the one column over. But I need to borrow from that 3 to the column one more over from that. So this 3 will now become a 2, and this 0 will become a 3, because when we borrow in base 3, we borrow 3. And then I'm actually able to do the subtraction. So 3 minus 1 is 2. 2 minus 1 is 1. So this is 1, 2, 2, base 3. All right, so let's take a look at another way of doing this using a different method. All right, so as we discussed, there's absolutely nothing wrong in the 1s column. We can subtract that just fine. Agreed? Yeah. But the 10s column, where it would have been our 10s column, which is our 3s column, has this inability to do the subtraction as is. Right? It's too big on bottom, too small on top. So what we're going to do is we're going to add something to this so that we can avoid having to do that first, borrowing. The correct number to add is 2, 0. Do you know why? Does anybody see why? Right. If I have this 2 here in the 3's column and I have this 1 here in the 3's column, 1 plus 2 is 3, which makes this become 0 in this column and add 1 to the column on the left. So this actually, on the one on the top, I don't have to do much. I just have to do 1, 0, 2, 2. On the one on bottom here, so let me just jot this down over here to make amends with it. What I'm doing is I'm adding the number 2, 0 to the number 1, 1, 0. So this becomes a 0. The 1 and the 2 we chose because that becomes an additional 3. It has the ability to become a 0 in that column. And now I have the number 2, 0, 0 here. That still has a problem, though. It would still require a borrowing, right? So I can do one more time of doing equal additions. What would I need to add to the 2, 0, 0? Close. 1, 0, 0. Yeah. One more 0 on that because we want that 2 and that 1 to be in the same column. The number on the top becomes 1, 1, 2, 2. The number on the bottom, when I take 2, 0, 0 plus 1, 0, 0, well, the first zeros are here. 2 and 1 is 3. So that's 1, 3 carried, and a 0 in this column. So this is the number, whoa, this is the number 1, 0, 0, 0. Can I subtract 1, 1, 2, 2 minus 1, 0, 0, 0 pretty quickly? Yeah, it's pretty good. No borrowing and such, which was the point. So we have 1, 2, 2, base 3. I don't think equal additions works quite cleanly on this one because we had that 2 steps of it, right? The one that we did back here was really nice because there was only 1 step to do the equal additions on. So not all numbers work equally as well in different ways, all right?